Today I'd like to review with you all the major things we learned with nuclear. Your test on nuclear is coming up very shortly, and I want to make sure that you're great on all the fundamental concepts. This will be the highlights of all the things we covered, and hopefully you have all the details already, but I just wanted to make sure you knew the most important things. So the number one equation for nuclear physics is the most famous of all equations. It's Einstein's E equals mc squared. I want you to remember that m actually stands for the change in mass. The change in mass that takes place, and when you lose mass, that mass turns into energy. So what you do is when you have a nuclear reaction, you total up the mass of the reactants, you total up the mass of the products, and they will not be equal. You subtract the two. You see how much mass you lost. You always have to start with more mass than you end up with. You see how much mass you lost. You make sure it's in kilograms. You plug it in here, and it will tell you how much energy you get in joules for that reaction. I also wanted to make sure you had your summary of particles. I'm not going to spend too much time on this. This is an important thing to have handy. It's all the different particles you might run across in a nuclear reaction. And these are the way you write them in your nuclear reaction. All right? Neutrinos, protons, neutrons. I added this one on. If you have your chart, I would suggest adding this too. It's just some random isotope. X represents the chemical symbol. So for like oxygen, it would be an O. And then this is the isotope number. This is the standard way of writing it. The chemical symbol, the number of protons, and then A stands for protons plus neutrons. So if you have your handy chart, it's not a bad idea to throw this in there. I just didn't think of it when I did it before. Okay, then we want to look at balancing nuclear equations. And when you're trying to figure out what a particle is as a product or even as a reactant, the rule is that your atomic numbers, which are actually your charges, have to balance. 15 on this side means we need 15 on this side. So make sure the bottom numbers add up to the same thing on each side. Up top, same thing. You add these together. That is your number of nucleons, protons plus neutrons. And they must add up also. So we have 31. We need this to be 30, so we get a total of 31. Remember, protons can turn into neutrons, and neutrons can turn into protons, but you can't just have one of them disappear from the universe. Okay? So your total number of protons and neutrons must be the same on both sides, even though the number of protons might change and the number of neutrons might change. I want you to remember that protons and neutrons are not the final word. Protons and neutrons are made of quarks. Protons are two up and a down. Neutrons are two down quarks and an up quark. It's not important that you know exactly what quarks make up each thing, but make sure you know that quarks are the basis of protons and neutrons. They each have 3 quarks. I want you to remember that the nucleus is held together with a nuclear strong force. All of these positive charges are repelling each other. Nuclei should not be able to hold themselves together with just electricity and gravity. We need another force. It's called the nuclear strong force. And remember that it is the strongest force in the universe, but it is only a short-range force. So when the nucleus gets too big, these particles can no longer exert a nuclear strong force on the ones that are very far away from them. I don't think we ever mentioned the fourth force. So we have gravity, electromagnetism, nuclear strong. I neglected to tell you nuclear weak force is the fourth, and the nuclear weak force is what's responsible for flipping the quarks from up to down or vice versa. I want you to remember when you have your chart, if it does not have a half-life or decay mode, it means it is a stable isotope and it will be around forever. When you see it has a decay mode and a half-life, that's an indication that that isotope will not be around forever and might spontaneously decay into a different isotope, hopefully one that is stable. If not, they'll keep decaying until it finds a stable isotope. I want you to remember the 4 different ways that we could have particles shoot out. This happens with big nuclei, and they shoot out alpha particles. This makes the whole nucleus a little bit smaller and more stable. We have beta positive, where a positive electron, a positron, a kind of antimatter, shoots out of the nucleus. This happens when a proton turns into a neutron. This happens with things that have too many protons. If it's got too many neutrons, then an electron shoots out of the nucleus, and one of the neutrons turns into a proton. We also have gamma, which does not actually change the isotope. It just lowers the energy of the isotope and making it a little more stable. Don't forget that there are neutrinos that can pop out. They don't have mass, they don't have charge. So just like the gamma, they don't really determine what the new isotope is going to be. Okay, but they must pop out to keep the nuclear spin constant. And remember that they travel almost at the speed of light and they have almost no mass. They can go right through the entire Earth most times without hitting any type of matter and being absorbed. If you had to find the speed of the particle, remember you do your E equals mc squared. Make sure you're working in kilograms, your answer's in joules. Put that into kinetic energy, equals 1/2 mv squared. And this is the mass of the alpha particle. Remember, the velocity you get will be approximately correct. It's not quite perfectly correct because some of the kinetic energy goes into the recoil of the larger nucleus. The larger this nucleus is, the more accurate this model will be. Okay? So the loss of energy turns into kinetic energy. How stable is your isotope? So again, when you see half-life, that tells you the time, on average, for half of the radioactive sample to decay. You never know which ones are going to decay. You never know when exactly they're going to decay. But on average, when one half-life passes, half of them will go away. Another half-life, another half of what was left. If you have a large enough sample, there's always a chance that some of them are still remaining. This is what the half-life graph looked like. Again, you start by looking at your starting value. You cut it in half, and you see how much time has passed. If you want to find a more accurate one, don't just do it once, but do it multiple times. Cut across, see where you are. Both times we get 60 seconds as the gap required to get half of it to disappear. So we can be pretty confident that the half-life is 1 minute. Remember, it will never mathematically hit 0. It gets closer and closer and closer. Don't forget, activity tells you how many decays there are per second. It can be measured in becquerel, which literally means decays per second, or the more commonly used but less helpful, Curies. Remember that we can artificially take a stable isotope, hit it with stuff, and turn it into something radioactive. We do this in the nuclear medical field. Remember, fission is where you take a big isotope and you break it into smaller pieces. This is found in power plants and the first atomic weapons. Fusion is where you take smaller stuff and combine it together to make bigger stuff. And this is what we have for a hydrogen bomb. And this is what we have for the power source of the sun. This is also a potential power source of the future because the fuel is abundant and the byproducts are perfectly safe. Okay? The difficulty is containing this reaction because it required such high temperatures. These are the major ideas we had with nuclear physics. And hopefully you remember not just these major ideas, but some of the minor things that went along with them. All right, so good luck on your test.